In our previous analysis of the CES-derived demand, we ended by noting the feature that the CES-derived demands are always interior solutions. In some applications, we might want to allow the demand for some goods to be zero, but we won't be able to get this feature from Cobb-Douglas or a CES utility function. As we will see in this video, this feature arises from the log-linear utility function very naturally. Now let's delve into the problem directly with our Lagrangian method. First, we're going to write down the optimization program with the max operator and the utility function, our control variables Q1 and Q2, and the budget constraint. Next, just like before, we can write down the Lagrangian based on this maximization program, which is just the objective function plus lambda times the modified budget constraint. Now, with the Lagrangian in place, we can take first-order derivatives with respect to the two control variables Q1, Q2, and lambda, and that will give us three first-order conditions once we set these derivatives to zero. In this case, because the utility is linear in Q2, the marginal utility is particularly simple in equation 2 here, which is just 1. We can then proceed with the same process that we're used to by now, trying to combine the first two first-order conditions into one equation. We can divide the left-hand side by the left, right by the right. Now, notice that this is a particularly simple equation that only contains Q1 and not Q2. So just by rewriting the tangent condition itself, we have already solved for Q1 in terms of the prices and prices alone. And because this term only consists of exogenous variables, this is a solution for the optimal consumption level of Q1 star. So now we can plug in Q1 star into the budget constraint and try to solve for Q2 star. And of course, when Q1 is taking this particular value, we can just subtract the expenditure on good 1, and then by dividing the remaining expenditure by the price of good 2, and that will yield this particular expression here as the solution. This problem now appears exceptionally simple. By using the Lagrangian approach, we found that the optimal solution for Q1 and Q2 that maximizes utility functions subject to the budget constraint are given by these two expressions here, Q1 star and Q2 star. Now let's inspect them a little bit more. We notice that Q1 is always a positive quantity because the prices are always positive. But what about Q2 star? Well, it is not immediately obvious that Q2 star is necessarily positive. And certainly, under the context of our model, where a consumer chooses the quantities to purchase that best suits their preferences, it is very strange to have a negative quantity. So, is it possible that Q2 star is negative? Let's check that. If Q2 is negative, and we know that Q2 star is taking this particular expression, then we can rewrite this inequality slightly by isolating out y to the left-hand side of the inequality and moving this term of 4 times P2 over P1 to the right-hand side of this inequality, and then by multiplying both sides by P2, which is a positive quantity, the sign of the inequality does not change, and we're left with y on the left-hand side and the right-hand side by 4 times P2 squared now over P1, because we're multiplying P2 on the right-hand side too. If necessary, please take out a piece of paper and verify that algebra. Notice that this inequality is true if and only if Q2 star, which is this expression, is negative. They are entirely equivalent to each other. The benefit of the right-hand side inequality is that it allows us to think of y somewhat separately from the prices of P1 and P2. And let's do that. For instance, if we imagine that the prices P1 and P2 are fixed, then the right-hand side of this inequality would be fixed. So it would just be a given number. Let's say P2 is equal to $2 and P1 is equal to $1. Then the right-hand side of the inequality will be 2 raised to the power of 2, which becomes 4, times 4, which becomes 16, divided by 1. So the right-hand side of the inequality would be 16. Now, if the consumer's budget is greater than 16, then this inequality would fail, meaning that the consumer's choice of Q2 star will not be less than 0. In other words, the consumer would actually purchase a positive amount of Q2. However, if the budget is lower than 16, then this inequality would hold, meaning that Q2 star will now become negative. In other words, our solution that we just found through the Lagrangian approach is now prescribing a negative amount of Q2 to maximize the consumer's utility. In other words, Q2 star becomes negative if Y is low relative to this modified ratio between the two prices of P2 and P1 on the right-hand side of the inequality. A slightly different scenario we can imagine is if we fixed Y but allow P2 and P1 to change. When Y is fixed, the left-hand side of this inequality is a constant. For instance, if Y is equal to $16 and P1 is at $1, then when P2 gets more expensive, let's say greater than $2, then the inequality will hold because the right-hand side will be greater than 16, whereas the left-hand side is at 16. In that case, it would suggest that our prescribed Q2 star becomes negative again. And our solution is now again prescribing a negative quantity for the consumer to maximize utility. On the other hand, if P2 dips below $2, then the right-hand side will be less than 16, which is the value of the left-hand side, and then Q2 star would be positive. On the contrary, if P2 is fixed at $2 and Y fixed at 16, then the inequality will hold if P1 is lower than $1, but will fail if P1 is greater than $1. In other words, the optimal solution prescribed by the Lagrangian approach is negative if P2 gets more expensive or P1 gets more inexpensive. To take stock, we realize that the prescribed optimal solution for Q2 can actually be negative when the income Y is relatively small, or if good 2 becomes relatively expensive comparing to good 1. So, what can be an interpretation of a negative quantity, at least at face value? Well, we can imagine that as the budget becomes tight, or when good 2 becomes expensive relative to good 1, the consumer may want to spend all their budget on good 1 and good 1 alone. And to go a step beyond, the consumer may even want to sell good 2 at its current price of P2 in order to raise more money to buy good 1. And it may turn out that such an arrangement would maximize their utility. Although somewhat intuitive, this scenario is at odds with the premise of the utility maximization problem in a common situation, where we're trying to model a standard consumer who is usually unable to sell things back to the store at the same price that the store would charge them. And that doesn't even take into account of the issue that the consumer typically don't just have extra goods ready to sell as the price fluctuates. This situation may be a possibility if there are investment goods, but for consumption purposes, it is quite unnatural to have negative quantities. So, How can we reconcile the premise of the model where the consumer cannot sell goods with the optimal solution we obtained? Well, in this case, we can impose a non-negativity constraint on top of the budget constraint that we already have. The non-negativity constraint would require that the quantities of the goods must stay at 0 or above. In other words, whenever the prescribed P2 star is negative, we will force it to be the lowest we would allow, which is 0. In other words, a negative quantity in good 2 would provide a higher utility, but we cannot allow it. So we will let Q2 star be the closest possible to that optimal negative solution, and that is 0. And now we will have a corner solution. The graphs here summarize the two different scenarios we just discussed above. When our budget Y is sufficiently high, or if P2 is relatively inexpensive relative to P1, then the optimal solution is an interior solution, exactly as what we have solved from the Lagrangian approach. The consumer will choose a positive quantity for both good 1 and good 2. The tangent condition holds on the budget constraint at a point where both Q1 and Q2 are positive. However, if Y is not sufficiently high, or if good 2 is expensive relative to good 1, then we start to run into this right-hand side scenario. When the indifference curve is tangent to the budget constraint, this tangent point lands on a negative quantity of good 2. This choice would maximize the utility of the consumer if the consumer could actually choose a negative quantity for good 2. But it is not allowed by our implicit restriction on negative quantities. So the next best choice for the consumer that we can allow, when we also respect the non-negativity constraint, is to choose Q2 star equal to 0. Choosing any positive quantity of good 2 would have landed on an even lower indifference curve, providing less utility for the consumer. So the best thing the consumer can do when it's restricted by the non-negativity constraint would be this corner solution here to choose Q2 equal to 0 and spend the entire budget on good 1. So the optimal solution for good 2 will be 0, and the optimal solution for good 1 will be the quantity of good 1 the consumer could purchase when they use the entire budget on good 1, which is exactly the Q1 intercept of the budget constraint. In this problem, we saw that the quasi-linear utility function offers the possibility of the consumer choosing a corner solution. Whether the optimal consumption bundle is in the interior solution scenario or the corner solution will depend on the exogenous variables Y, P1, and P2 that defines the decision environment. As the decision environment changes, the optimal choice of the consumer may move from the interior solution to the corner solution, or the other way around. We saw that this feature brings some extra burden in our analysis, but it offers another level of richness that's suitable for some applications, especially when the consumer may not use up all the budget on the goods. In this type of applications, the good that enters linearly in the utility function can be used to model cash. For instance, in modeling consumers' choices over a group of similar alternatives, let's say different types of breakfast cereals, you can imagine that a quasi-linear utility function with different cereals entering the utility function in a nonlinear way, whereas a cash good enters linearly, just like the Q2 we have in this utility function. In some cases, the consumer might not end up using all the breakfast grocery budget on breakfast cereals. So the cash good will be strictly positive at the optimal choice, meaning we have an interior solution. On the other hand, if it is optimal to spend the entire budget on different types of cereals and no other food, then the cash good becomes a corner solution, meaning that the consumer uses no cash in the budget on goods other than cereal. We will sum up the utility maximization problem with two more examples of our extreme forms of utility functions: perfect substitutes and perfect complements. You will see that in neither case will the Lagrangian approach work, and we will have to reason our way through. As we've discussed before, if two goods are perfect substitutes, then the indifference curves are straight lines. So the slope of the indifference curves are almost always different from the slope of the budget constraints, unless they're perfectly parallel. So in these scenarios, the tangent condition won't help us locate the optimal solution, which means the Lagrangian approach won't do much. On the other hand, if the two goods are perfect complements, then the indifference curves are perfectly angled at 90 degrees. And their slopes are undefined at these turning points. And because the derivatives are undefined at those points, so the first order conditions can't help us anymore, which means that the Lagrangian approach won't apply. As a result, we'll have to go back to basic intuition that we have been building so far and try to maximize the utility through reasoning. For the perfect substitute case, we illustrated on the left-hand side graph, we can see that if we pick any point along this budget constraint, let's say this point A here, we can always improve on this consumption bundle by sliding down the budget constraint and moving up to a higher indifference curve. And the highest indifference curve we're able to reach will be the one that's passing the Q1 intercept here. So the optimal consumption bundle will be at the Q1 intercept, where the consumer spends the entire budget on good 1 and nothing on good 2. But what is the economic intuition behind this solution? Notice here that the indifference curves are always steeper than the budget constraint. In other words, the absolute value of MRS is greater than that of MRT. Or U1 over U2 is greater than P1 over P2. If you rewrite this expression into the per dollar marginal utility form, then we have U1 over P1 is greater than U2 over P2. This means that the per dollar utility for good 1 is always greater than that for good 2. If we recall our intuition from the apple jar, banana jar thought experiment, good 1 in this case always provides a better bang for the buck than good 2. So the optimal consumption choice for the consumer should allocate the entire budget on good 1. We can use a very special example to verify this intuition. In this particular example, good 1 is a can of Coca-Cola and good 2 is a can of Pepsi. If these two goods are indistinguishable to the consumer, then they probably have the same marginal utility. Now suppose that good 2 is more expensive than good 1. How will the consumer choose their optimal consumption bundle between these two goods? Well, of course, the consumer will spend all the budget on good 1 because it is cheaper. In this particular example, the absolute value of MRS is 1 because they have the same marginal utility. But the absolute value of the MRT is P1 over P2, which is less than 1 because good 2 is more expensive than good 1. And quite intuitively, good 1 offers a better bang for the buck. You see that our intuition from the models to think in terms of MRT and MRS covers this special case, but also extends generally to cases where the two goods don't have the same marginal utility. I will leave these cases to practice. Now let's turn to the perfect complement case on the right-hand side. Let's ignore this light colored curve here, labeled as L2, which is an alternative budget constraint. We will talk about this curve later on in the next section. If we just focus on this darker budget constraint, L1 here, we can directly see from the graph that the optimal consumption bundle will be the point on this budget constraint that exactly sits at this corner of the indifference curve I2, or point B here on this graph. Point C would provide a higher utility, but it is beyond the budget. Point A is within the budget, but we can improve on it, obviously. In fact, I would argue that for perfect complements, if we allow the consumer to buy any arbitrary fraction of the goods, then the optimal consumption bundle is always on the corner of an indifference curve. Why does this have to be true? Let me discuss a technical explanation first, and then a more intuitive one. Let's consider a consumption bundle that is not at the corner of an indifference curve, but is on the budget constraint. Let's say this blue point here on the budget constraint. Because this point is not at the corner of the indifference curve that passes through it, therefore, it must sit somewhere along one of the two perpendicular arms of the indifference curve. Let's say it sits on the vertical arm. Then what that means is that we must have a corner point somewhere inside our opportunity set. And we can have another horizontal arm sort of extends towards the right like this. But then it means this blue point is just providing exactly the same level of utility as this red point within the opportunity set. And we can always improve on that by choosing any point inside this opportunity set here in this little corner towards upper right of this red corner point. Our argument essentially shows that any consumption bundle that's not lying on the corner of an indifference curve can be improved upon. Therefore, the optimal choice must be at the corner. Mathematically, the utility function for perfect complements is taking the minimum between two objects, some modified version of Q1 and some modified version of Q2. A corner on the indifference curve means that both terms in the minimum function should have the same value. In other words, we never want to have redundant units in one good that does not increase utility. The resources used on the redundant units can be freed up to spend on the other good, which restricts the utility level. So instead of buying one bicycle frame and 6 wheels, maybe a better way to use a budget is to buy 2 fewer wheels so you can free up some budget to get another frame. This way, you might be able to get 2 frames and 4 wheels, which will make 2 complete bikes. Through these 2 very special examples, we can make 2 observations. First, when calculus does not work, analyzing the problem is hard. This is a good illustration of the power of calculus in economic modeling. Second, although calculus does not work in these cases, the intuitions we built up through all these previous examples actually generalizes to a large degree to these cases as well. And they provide a framework that guides our understanding of these problems. Hopefully, these ways of thinking will help you in understanding different models in analysis and also different scenarios in life.